So for another session of that, we're planning towards the end of January to start. We will do the last Friday of the month, but we will keep you posted. We will send the announcement on demand, etc. But in order to finish well this season, we have Yuan Zhou with us today. She's an associate professor in the Department of Mathematics at the University of Kentucky, and she earned her Diplôme d'ingénieur from the École Centrale de Paris, and also a master's degree in applied mathematics from Université Paris-Dauphine in 2012. And then she received the PhD in applied mathematics from the University of California in Davis in 2017. And now her research focuses on polyhedral geometry, cutting planes, and in particular, cut-generating functions for integer programming. The floor is all yours.
Oh, thank you. Thank you for the invitation. I finally was able to make it, and let me share my screen. Let me know if you can hear and see. Great. So let's get started. It's my great pleasure to be here talking about our recent work on all-cyclic group Facets Inject. And this is a joint work with my former PhD advisor, Matthias Kappa from UC Davis. So I usually work in cutting planes and more specifically cut-generating functions. I will introduce what that is. Then a specific problem about the name master group relaxation, where the master comes from. All right, so suppose we are given a pure integer program. We use the LP relaxation first, solve it by simplex method. We get the optimal dictionary, and we observe that the current optimal solution is fractional, so not feasible to the original IP. We want to find cutting planes. One way to do that is to use the so-called cut-generating function, and it's a framework introduced by Gomory Johnson in the 1970s. What is it? Well, we take one row from the optimal simplex tableau for the LP relaxation. Consider y as the non-basic variables. They are integers, non-negative integers. Now we do a relaxation on the basic variables. We relax positive integers x to just integers. That is, we read the row by modulo 1. Now we consider all solutions y satisfying this group equation. This is usually called the corner polyhedron. The corner polyhedron is the convex hull of solutions y, such that the group equation r times yr summing over all r in the finite group P is equal to the right-hand side constant f. In our example here, f is minus 1 over 5, and P is the finite group containing 1 over 5, 2 over 5, and 4 over 5. We consider valid equations like pi, so that the sum of pi r yr summing over r is greater or equal to 1. This inequality is a cut. Currently, the basic solution has all y's equal to 0, so the left-hand side of the new inequality greater or equal to 1 is not satisfied, and it cuts off the current optimal solution. If we have such function pi, we can apply it to the tableau row and get a cut. Our question is, what are such function pi's and what are good ones? Before saying which ones are good, let's think about a more relaxed problem called master group relaxation. So instead of just 3 right-hand side non-basic variables y's, we now introduce every y for on a grid of 1 over 5. The 5 comes from the common denominator of the data in the tableau. This is called the master group relaxation. We can see the tableau row is just restricting the non-appearing y's to 0. So if we are able to find a pi that works not only for the group relaxation, but also for the master group relaxation, then applying it to the current tableau will give us a valid cut. So in a sense, the master group relaxation and its cut generating function pi is more general. Gomory and Johnson considered even one further relaxation. So now looking at, we ignore the denominator and we allow any real value. That is, we consider infinitely many right-hand side variables y, and we are looking for function pi still in the form of pi r yr, summing up this greater or equal to 1. This is a valid function, and now it is valid for the infinite group relaxation. Infinite group relaxation is the convex hull of all y's satisfying the infinite group equation. This is even more general than the finite group, cyclic group relaxation. So let's now look at a toy example to see how cut generating functions such pi perform on a particular problem. We open the textbook, find a cut generating function, maybe the most famous one, Gomory mixed integer cut. For the finite group problem defined on the grid, the cyclic group of order 5, it is a discrete function. For the infinite group relaxation, it will be a piecewise linear function. The specialty of this function is it has 0 on the integer values, has value 1 on the special right-hand side 1/5, and it is periodic. Now, these are all come from textbook, and we can now apply the function pi to the coefficients in the tableau row in order to get coefficients for a valid cut. For instance, we take the coefficient in front of y1, which is 205, look up the function value pi at 205. It is on both sides 3/4. So we get the coefficient of y1 in the cut. The first term is 3/4 y1. For y2 in the tableau, it is -1/5, and pi of -1/5 is, well, because of modulo 1, it is the same as pi of 4/5, and this value is 1/4. So we obtain the second term in the cut inequality, and so on and so forth. Adding the 3 terms up, making it greater or equal to 1, we get the cut. So we want to study the structure of the corner polyhedra, also in the group and infinite group relaxation. We want to look at the dual side to find valid inequality that define that polyhedra. As in polyhedral geometry, instead of merely valid function, we are more interested in tight valid functions and even the facet defining functions. And all these notions are brought into the Gomory Johnson's group relaxation framework for the cut generating functions. We have the valid function we just introduced, then the minimal functions. The minimal ones are the valid function that is not dominated by others. So there is no other valid function strictly smaller than it pointwise. And according to a classic theorem, the minimal valid functions are very well defined, classified. They are exactly the non-negative functions satisfying 3 properties. One has pi 0 is 0, pi f is 1. Second, pi is subadditive, meaning that taking any xy, pi x plus pi y minus pi of x plus y, this is the subadditivity slack function, and it should be non-negative. The third condition is pi is symmetric. So we know the minimal functions quite well, but for the analog of facet, here we have the extreme function. The extreme functions is a minimal function that is not the convex combination of 2 other minimal functions. So on the left-hand side, the graph shows a minimal function because it satisfies all the 3 criteria, but it's not an extreme function because it can be written as 2 other functions that are minimal. And in this talk, I will use interchangeably extreme function or facet defining inequality facets. Okay. What are the relation between different notions in finite and infinite group setting? Well, according to a classic theorem, the restriction of a minimal function for the infinite group problem is a minimal function for the finite group problem. And the interpolation of a minimal function in the discrete setting for the finite group problem is minimal for the infinite group problem. However, this two-way implication is not true for extreme function. When we have an extreme function for infinite group problem and we restrict it to the grid points, then it is extreme for the finite problem. However, the other direction is not true. The interpolation of an extreme function defined for a cyclic group is not extreme for the infinite group problem. Here we have a tiny example. And for the other direction to work, one needs an overexampling factor of at least 3. So here's our question. We are mainly interested in answering, well, given a extreme function for the finite group problem of cyclic group order Q, is there always an extreme function for the infinite group problem so that restricting the piecewise linear function phi to the grid point will give the finite function? Before answering it, let me give a few words on why we are interested in it. Well, it is known that if we have a finite group problem looking at the facets, the extreme function for the finite group problem, now we refine it to a finer grid, then the causal grid function is arise from the finer grid. So more specifically, any group, the facets from a finite group problem arise from the master problem, where the master problem is a where the finite group is a subgroup of the master group. So what this means is, well, you have a function, then refine the group. You can always find an extreme function for the refined group so that restricted to the causal grid, it is extreme. It's the given function. And now refine this grid more and more. This will lead to an infinite group problem. So it is natural to think, well, whether we have an extreme function for the infinite group problem, when restricting to the grid, it agrees with our given function. Surprisingly, this is not answered as far as I know. So we were able to show the infinite master theorem for facets. That is, all facet pi of a finite group problem arise from facets of the infinite group problem by restriction. And for the infinite group problem, we can take that pi as, in particular, piecewise linear continuous with 2 slopes. When justifying this theorem, we will see that the infinite group problem is the correct universal master problem for all cyclic group relaxations, if we are interested in cut-generating function and facets. So how do we show our main theorem? Well, there are some gradient already well known. Gomory Johnson already showed that given a valid manual function, if it is continuous and piecewise linear and only has 2 slopes, then it is already extreme. Also, given a minimal function, it is possible to make it additive and with 2 slope and piecewise linear with 2 slope so that on the grid points, they agree. However, the new function through the 2 slope lifting is not extreme. So it does not play the role of our theorem. Yet we also know an approximation theorem. Given a continuous minimal valid function, we can approximate it by another function that is extreme, that is continuous piecewise linear with rational breakpoints and two slopes. However, the construction in this theorem does not preserve the function value at the grid point, so also not good to prove the master theorem. Let's take a quick look how this construction goes. Well, we want to approximate a given function by two slope function and make the new function extreme. The first thing Hildebrand, Basu, and Molinaro did is to wiggle the function a little bit so that the subadditivity slack is strict. Then on the new function, blue function, use the two slope lifting to make it continuous and only with two slope. Then to make it extreme, it also need to satisfy the symmetry condition. So flip half of the yellow function to make that happen. As a result, the new function through the symmetric two-slope fill-in is symmetric, even extreme, not far from the original pi with two slopes, but it's not an its restriction to the grid point is not the original function. So in our main theory, we propose a variant of the previous symmetric two-slope fill-in. We propose the so-called injective two-slope fill-in. And the specialty is it will preserve the function value on the grid point so that we show the infinite group problem is the true master problem for all cyclic group. Specifically, we take minimal function pi, continuous piecewise linear with rational breakpoints and only rational functions. And for any small epsilon, there exists a function phi through the injective two-slope fill-in, so that the new function is continuous piecewise linear only with two slopes. So it's going to be extreme for the infinite group problem. It is very close to the original function, and more importantly, on the grid points, also refined grid points, phi agrees with the original function pi. I'm going to give a rough idea of the construction. Well, so we are given pi, a finite group valid function, minimal function. Extreme function for the finite group problem. So this defined on the rational points of cyclic group order Q. We first interpolate into a continuous function. It has breakpoints in 1 over QZ. This is the first grid, 1 over QZ. We now look at where function pi takes value 1/2. And these are the points we want to make to a refined grid. Here we refine the grid from 1 over 9 to an oversampling factor of 10, so 1 over 90. The first thing is to ensure the 1/2 value lies on the grid. Then we will take another refinement so that when we lift it, fill in with two slope, the modification is so small. And this is through a careful selection of large integer multiplier of R. R is a multiplier of Q. Then we choose another larger multiplier of R to make the grid finer. And then on the grid of 1 over RQ, we are going to use a similar process, adding or subtracting a positive tent, a very small length, to the function, given function pi to make it two-slope continuous, and we are going to show that whether adding or subtracting a tent depends on the current function value compared to 1/2. Namely, if pi x is less than 1/2, then we add a tent to get phi. If pi x is currently greater than 1/2, then we subtract a tent from pi to get phi. And if it is 1/2, then we look at where it lies, if it is compared to this special right-hand side constant f over 2. So already from this construction, we can see a new function phi is periodic and symmetric. It agrees with the original function pi on a more refined grid of 1/mq. It has two slopes, the most positive slope x plus and the most negative slope s minus, and some detailed property of where it is linear and the difference of phi and pi. It is a constant on each grid of length 1/rq. And because we can take the refined grid so small, the difference between phi, the new function, and the original function pi, we can make it arbitrarily small. As a result, the new function is non-negative. So what we really need to do is it remains to show that the new function is subadditive. And then it's true that this phi is what we want that can show the theorem. And the difficulty lies in showing phi is a subadditivity function. It contains many cases, and we are going to analyze all of them. Of course, we're not, so case reduction is needed. So the object of interest is the subadditivity slack. It has 2 dimensions, and we are going to reduce many cases to the canonical ones. We already know that because of the piecewise linearity, it is periodic. And we just use this property and look at the canonic triangles of grid length 1/rq, where pi is affine linear. Taking x from a grid of 1/rq, y from a grid of 1/rq, then this defines a triangle F. Because of symmetry, we only need to consider the lower triangles. And then use the affine linearity of pi, we get that the subadditivity slack of pi is also affine linear over the triangle. If the subadditivity slack of pi is strictly greater than 0, then because phi is an approximation of pi, the difference is very small. We can already say that subadditivity delta of phi is non-negative. So we may add the assumption that there is an vertex UV of this triangle F prime where subadditivity of pi is 0. Now, we are going to look at the final grid 1/mq, where the new function is periodic. And we tile the larger triangle F by the smaller ones. We don't need to look at all the smaller ones, but just the ones next to or closest to the additivity vertex U and V. This just follows by calculation and subadditivity of the original function pi. Then we distinguish in the construction if we add or subtract a tent to phi, and maybe distinguish 4 cases and use some lemma depending on the construction the length of the subinterval where phi takes positive or negative slope. And the detailed proof is quite long, but it is manageable after the case reduction. It is doable in maybe 10 pages. Anyway, if you trust me, we showed the theorem that all facet pi from finite group problem arise from facets of infinite group problem by restriction. It is still open that whether we can generalize it to arbitrary dimension and to arbitrary finite group problems. Here we take finite group that is a subgroup of cyclic group. In addition to that, maybe the master infinite group theorem also answers clears doubts on in a separate direction regarding the extremality of limits of extreme functions. So now we take a sequence of functions. If each function is minimal, then taking limit, it also is a minimal function. But extremality is not preserved by taking limit. Previously, we know there exists sequence of continuous piecewise linear extreme functions that converges pointwise to discontinuous function, and the discontinuous one is not extreme. We also know there exists sequence of piecewise linear extreme function with rational point that pointwise converges and converge uniformly to a non-extreme function. With this new construction, we can show with the further addition of, converges uniformly and converges to continuous piecewise function. We can also find sequence of continuous piecewise linear extreme function with rational point that converges uniformly to non-extreme continuous piecewise linear with rational points. And this is just a corollary of the injective approximation theorem, because eventually we can take, on rational points, we can take a grid finer and make the newly constructed function phi agree with the original function on all rational points. So eventually the newly constructed sequence phi I will become constant. Okay. And the calculations, verifications manually is quite tedious. So we made everything regarding the cut generating functionality available as a package. And Matthias is very interested in maintaining and publishing it as a library of Sage Math package. Yeah, I think that's all for this talk. I'm going to stop it here. And any question is very welcome.
Thank you so much, Yuan.
Are there any questions from the public? You can either write them in the chat or just start speaking, unmute yourself and ask your question. In the meantime, I have one. So this all works in the setting where you consider one line of your tableau that is not What if by any chance you would consider two lines?
That's a great question. Actually, our construction only is for one row of the tableau, so one-dimensional cut generating function, and we don't know how to generalize it to higher dimension because so many cases. Although the previous Basu Hildebrand Molinaro's construction, they can show it works for dimension. Sorry.
That's why because I remember that result and I was wondering if there's how big of a pain is to extend also yours to higher dimensions?
Yeah, that's a great question. It's open. We don't know how to modify the construction for higher dimensional case.
Okay. Well, thank you. And if there are no questions, I'm sure that Yuan will be available to answer them by mail, just in case. And thank you again for joining us. And we hope to see you all next season of Dots.